I want to do a quick series of videos today about parallel RLC circuits. So parallel RLC circuits are containing resistance, inductors, and capacitors. Not all parallel circuits are going to contain all three, but if we can solve one with all three, then we shouldn't have a problem solving one with only two. So the first step in parallel RLC circuits, step number one, is to solve each branch. Now the key is to just do a little bit at a time and work our way towards the end. Trying to look at the whole question at once is going to be a little bit overwhelming. So if we're trying to solve each branch, we can figure out the current that is flowing in each branch. So in this case, I've got 240 volts and a 15 ohm resistor. I can go I1 equals V1 over R. In this case, I get 16 amps. Perfect. Now that's easy because it is a resistor. No problem. When I move into this coil, it gets a little bit more complicated because I have that resistive component as well as the inductive component. So what we have to do for our coil in this circuit is we actually have to create Z of the coil, a little triangle. We have to figure out, we have to put our resistive component here, and we have to figure out what our XL is. We can solve our XL by going XL equals 2 pi FL. And in this case, we get 10.8 ohms. Once we have our resistance and our inductive reactance, we can figure out the Z of our coil. In this case, Z equals 18 ohms. Now, once we have the Z of the coil, we can figure out the current that is flowing through this branch. We can use 240 volts, which is the voltage across the coil, multiplied by, or divided by the impedance of the coil. So we'll go I2, we'll call it in this case, flowing through the second branch, equals V2, 240 volts, divided by Z of the coil here, which in this case gives us 13.333 amps. Perfect. Now, because our coil is resistive and inductive, we actually have an angle here for that branch of the circuit. Now, we can solve that angle in any ways. So SOHCAHTOA, you can figure out the power factor. What I've calculated it out to at negative 36.87 degrees. So now that's the angle of the coil. The last branch is our capacitor. We have a microfarad rating, 66.314 microfarads. So we can go XC equals 1 over 2 pi FC. In this case, we get a capacitive reactance of 40 ohms. Now, once we have that capacitive reactance of our coil, we can figure out the current flowing through that branch. We can go I3, because it's the third branch, equals V3 divided by XC in this case, and we end up with 6 amps. Now we're going to take these values and we want to place them onto an HV chart, and then in the following video we'll take those values and we'll figure out our current total, and then in the video after that we'll take these values and we'll work with power. This is 6 amps. So before we put it onto our HV chart, just to refresh, because our 16 amps is across a resistor, it's actually going to be in phase, meaning this is going to be at 0 degrees. We said that this was out of phase a little bit because it's at negative 36.87 degrees. And our 6 amps across our capacitor is going to be at 90 degrees. And the reason we know it's at 90 and at a negative value is because we know in an inductive circuit, our current is lagging our voltage, and in a capacitive circuit, our current is leading our voltage. Well, in this case, on a phasor diagram, our voltage, we're going to call our reference, because our voltage is the same throughout, 240, 240, 240, 240. Voltage is our reference. I1 is going to be at 16 amps. And it's going to be in phase. I2 is going to be the current flowing through our inductor, which we said was 13.333 amps at negative 36.87. And finally, our third current is 6 amps at positive 90 degrees. So that's step one in our parallel RLC circuits, is to solve each individual branch using the opposition to current flow in that branch and the voltage in that branch to figure out the different current values. Thanks for watching. Remember to check out the next videos to solve current total for the circuit and power totals for the circuit. Thanks. Hi, welcome back. This is the second video in our parallel RLC series. What we're going to do now is we're going to take the current values which we solved in the last video in our 3 different branches, and we're going to combine them and we're going to solve for the current total in the circuit. So just like every parallel circuit, our I total is going to be I1 plus I2 plus I3. Only now we have I1 occurring at 0 degrees across the resistor, I2 occurring at negative 36.87 degrees across the coil, and I3 at 90 degrees across the inductor. So what we do is we take these 3 values, I1 plus I2 plus I3, we're going to put them into a HV chart. So we're going to add up all of our horizontals and all of our vertical values. So we get 16 amps, keeping in mind H is the cos function, and V is the sine function, and 0, we get 10.666, and we get negative 8. It's a negative angle, so make sure when you're putting it into your calculator you use that negative angle, or you go 360 minus 36.87 to get that proper angle. And then here we get 0 and positive 6. So we add up all our horizontals, 16 plus 10.666 gives us 26.666. And we add up our verticals, negative 8 plus 6 gives us negative 2. Perfect. So what we've done is we've taken all that info and we've said, okay, if I'm starting here, I'm going over 26.666 and then going down 2. So we're making our own little current triangle. Perfect. We can use Pythagorean's theorem and figure out our IT, which would be right here. It's 26.741. So we have IT equals 26.741 amps. To figure out our angle, we use any one of our SOHCAHTOA functions, and we should get negative 4.292 degrees. So that's this guy right in here. And the reason I know it's negative is because my total out of phase voltage is a negative value. So now our last step is to take that, our IT, and bring it over here to our phasor diagram. So IT will be somewhere around there. Perfect. So that's what we do to solve for IT in this circuit. Now the last thing I want to talk about really quickly is the total impedance for a circuit. Now the only way we're going to solve for total impedance in a parallel circuit is by going ZT equals ET divided by IT. We are not using any impedance diagrams for the entire circuit in parallel. I'll leave that calculation up to you guys. Thanks, and please watch the next video where we talk about power in parallel. Hi, I'm here to wrap up our set on parallel RLC videos with step 3. Now step 3 I think is the most versatile method for parallel RLC circuits. and it is using power. So we have to keep in mind a couple of the basic rules about power in both series and parallel circuits, which is our watts can add up. PT is going to equal P1 plus P2 plus P3. Also, our reactive power is going to add up. The reactive power in branch 1 plus the reactive power in branch 2 plus the reactive power in branch 3. Keeping in mind, sometimes they're occurring that 180 degrees apart. So in this case, I like to take my circuit and I like to do a power triangle for each individual branch, as well as I like to then combine all that information onto one power diagram for the circuit. So here, what I would do is I would look at the circuit, I would say, okay, 16 amps, only a resistor. I'm going to use my power triangle for that branch would look like this, and I'm going to say P1 is going to equal I1 squared times the resistance in branch 1. Now, in this branch, because it's a pure resistor, you could use I1 times V1, or you could use V1 squared divided by R, but this is my favorite formula, so I'm going to use that. In this case, I get 3,840 watts. So I'm going to actually put that information over here, 3,840 watts. Then I move along to my coil. Now my coil is always going to be the toughest part because it has both the resistive and the reactive components. But we know it's going to create its own little triangle. Up here, I'm going to go P2, power 2, equals I2 squared times the resistive component of the coil. Now it's very important that I'm using the current flowing through the coil and then only the resistive component of the coil, which gives me 2559.9 watts. Now I can go a couple places from there. I can use my power factor from my previous triangle when I did the Z, but my preferred way is I'm going to use the current squared times the reactive component. So I'm going to go Q2 equals I2 squared times X in this case, and I get 1,100 or 1,919.9 VARs. Perfect. Now, two ways from here. I can do some Pythagorean's theorem. Q squared plus P squared equals S squared. Or I can go S equals I2 times V2. 240 volts times 13.333 amps. Either way, I should come out around 3199.9 VA. So I can take my horizontal value and my vertical value and I can come put them over here. I got 2559.9 watts and I got 1919.9 bars. Now my last step is the power in the third branch across my capacitor. Because it's a purely reactive circuit, I know I'm looking at only VARs. In this case, I'm going to go Q3 equals I3 squared times the X in that branch. 6 amps squared times 40 ohms gives me 1,440 VAR. Now I know the capacitive reactive VARs and the inductive reactive VARs are occurring 180 degrees out of phase. So that goes up here, 1440 VAR. So if we wanted, we could call this QXC, and we can call this QXL. Now what happens, because they're occurring at 180 degrees out of phase, we end up with a Q net. In this case, I know my QXL is bigger, so I know that my hypotenuse, this triangle, is going to be going this direction. I can figure out my Q net by going 1919.9 minus 1440, which gives me 479.9 VARs as my Q net. My power total is going to be P1 plus P2. In this case, PT equals 6399.9 watts. So now I've created for myself a power triangle for the circuit. 6,399.9 watts, 479.9 vars. I can do Pythagorean's theorem, and I can solve for my S if I want. Or if I want, I can also go I total times V total or E total of the circuit, and I can get it that way as well. Whichever way I do it, I should end up with 6,417.9 VA. Perfect. Now the very last step with all of these circuits is my power factor. It's going to be watts divided by VA. So I go 6,399.9 divided by my VA, and I get a power factor of 0.997, which is actually a very good power factor. Well, I hope that helps. It's really, really important to remember that you can add up watts and you can add up vars, but you should never be adding up the VA. Thanks for watching.